Another important feature that you need to know from stereoisomers is how to figure out the relationships between two structures. The first thing that you must do is check the molecular formulas and then the connectivity of the bonds for both the structures. If the molecular formulas are the same and the connectivities are also the same, you cannot enlist them as constitutional isomers. They would either be same compounds or they may be stereoisomers. If there is a possibility of being stereoisomers, then at all the chiral sites, you should assign the R and S configuration. Let's look at these two structures. I tried to draw them out in a Sawhorse projection. So this carbon is in the front and this carbon is at the back. Similarly, this carbon in the front, this carbon at the back. At this point, I have to first figure out what is the molecular formula for structure A and structure B. And I find that the molecular formulas for both of these compounds is exactly same. Then I look at the connectivity. For my first carbon, I have two methyl groups and one hydrogen. For my first carbon, I have two methyl groups and one hydrogen. What about my second carbon? For my second carbon, I have one bromine, one chlorine, one hydrogen. For my second carbon in structure A, I have exactly same atoms, chlorine, bromine, and hydrogen. So my connectivity is exactly the same. What is the next thing that I want to look at? I'm now going to assign the chiral centers as R or S. Now, my first atom is sp3 hybridized, but all the four groups are not different. The methyl groups are exactly the same. So this atom is not a chiral center. Similarly, at this point, I have two same groups on the sp3 hybridized orbital carbon, and hence this carbon is also not chiral. But if I look at my second carbon, I have four different groups around it, and I can easily label it as a chiral carbon. Similarly, my second atom right here, I can label that also as a chiral carbon because four different groups are on it. This is when I will start to look at my R and S sequence. So to follow the R and S sequence, we will now give priorities to our four different groups. Looking at this carbon right here, bromine will have more priority than chlorine, then carbon part, and the hydrogen part. Now, if I have to redraw this all over again, I'm going to draw it something like this. And this group attached to my third carbon or the third group. What is the priority? My number 4 is at the back. Number 1 goes to 2, goes to 3. And so what is the orientation of my molecule at this point. And I would say this is anti-clockwise according to 1, 2, 3. If the face of the structure is there, and this can be considered as the back portion. If you cannot see that, you can still convert the places or switch the locations of number 4 and number 3, which are in the position, so that number 4 or this can be your back, and you can observe what happens to 1, 2, 3. So when you will see it from the back end, whatever you get at this point, you just reverse it. For example, if we get R at this point, we know we are looking at the wrong direction. I will use it as S. So this particular group, which I have here, can be labeled as S. Sorry, R. And look at this now. Number 4, 1, 2, and 3. Again, we can just look at the 4 bonds in this fashion because this part is coming out in the front. If you observe my bromine and chlorine and the hydrogen. So 1, 2, 3, 4. All I have to do is just put my 4 behind. So 1, 2, and 3. So I can see that I have a R motion again, of the clockwise motion again, which can be assigned to this particular molecule again. So far, if I have to look at the relationships, they have the same molecular formula, they have the same connectivity, and they have the same configuration also. What does this mean? It means both of these structures are the same compound. Looking at the definitions of all of these 4 different stereoisomers that we can have, it is only the enantiomers which need at least 1 chiral carbon. Enantiomers always exist in pairs. If there is a R, there will always be a S corresponding to it. Enantiomers need 1 chiral carbon at least, and they are non-superimposable mirror images. The best example of an enantiomer are your hands. Imagine there is this hand with the other hand. If you look at both of them, they are mirror images to each other. But if you want to superimpose them, they are non-superimposable. They can exist in RS combination, or if you have 2 chiral carbon sites, for example, in this structure, make sure that you first label each chiral site and then you name the configuration accordingly. If you have a chiral site of R and another chiral site of S, this particular structure's enantiomer should have exactly same compound with same connectivities, but at these 2 carbon sites, you should have exactly opposite configurations. So between structure 1 and structure 2, we see that the first carbon have opposite configurations and the second carbons also have exactly opposite configuration. So the RS and SR combination can be seen in these two structures. And we say structure 1 and structure 2 are enantiomers. Another set of examples which are enantiomeric pair are between these two structures. At the same chiral site R and the same chiral site, it is S. At this second chiral carbon, it is R. And exactly at the same chiral carbon, it is S. What we see is a RR-SS combination. So structures 1 and 2 are enantiomers to each other. Structures 3 and 4 are enantiomers to each other. On the other hand, diastereomers, which are more common than enantiomers, need at least 2 chiral centers. Since structure 1 and structure 2 have exactly opposite configurations at the chiral site, they cannot be diastereomers, but structure 2 and 3. So at this chiral site, your structure or your configuration is S. But at the same carbon on the other structure 3, it is R. On the carbon, second carbon of structure 2, it is R. And the second carbon of structure 3 is R as well. So what we see is a SR and RR combination. This is what a diastereomeric relationship could be. Structures 2 and 4 are also enantiomeric to each other. Structures 3 and 1 can also be enantiomeric to each other. Structure 2 and structure 3 are enantiomeric to each other. What about structure 2 and structure 5? They are exactly same compounds. Okay? Just like diastereomers, meso compounds also need at least 2 chiral centers. And there should be a plane or a point of symmetry. So if you look at this particular structure, if one of the groups will be R, the other will be S. Within the same structure, if your light is being rotated in one direction by one enantiomer, it will be rotated to another direction by the other enantiomer and to the same extent, because same molecules are present. There is a plane of symmetry here. So we know they are the same structures, same molecules, same groups around this particular chiral center. If one enantiomer is rotating the light, the plane polarized light in one direction, the other enantiomer will rotate the plane polarized light in the other direction and to the same magnitude, to the same amount. And hence overall, there will be no chirality for this molecule.